Hello, everyone. My name is Soumya Raghu. I am your TA grader for the EMCH 561, the Composites Manufacturing course. In this lecture, we are going to talk about the liquid injection molding simulation. And we are going to go over a few of the basic um, scenarios where we will be studying the resin injection through the mold um, and the software that we will be using is called LIMS. I'm going to now share my screen. That'll lead you to the website for LIMS. And give me 1 second. I need to do that. All right, so LIMS, as I said, is liquid injection molding simulation. It is a software that was developed in the University of Delaware by Dr. Tucker and Dr. Advani. And this software essentially helps us to simulate the flow of a liquid through a porous media. So in this case, we are going to study the flow of the resin through the fiber fabric preform, and we are basically going to simulate the flow before conducting the experiment. We know that from our basic knowledge that before conducting an experiment, yeah, to obtain the optimum results, we always conduct simulations to find out what the optimized characteristics of a specific phenomenon are. Similarly, our main purpose of using LIMS is before going on and taking up an experiment to impregnate a complex model, such as parts of a car or so on, or even for bridge building a competition, we usually try to model, let's say, a square beam or I-beam using LIMS and further impregnate the entire beam with the resin, so that we can optimize where the location of the inlet ports of the resin must be, so that we get no dry spots or no voids in along the entire mold itself. So as I said, this helps us to minimize the number of experimentations or number of iterations that we have to do to get an optimized, the optimized mold or optimized final product. And more details regarding GLIMS is given on this website. I've also added this on the PowerPoint presentation, so you should be able to log in and download the specific files that I'm going to say. So once you enter the website, there is downloads, which essentially has the all of the files that you need for performing simulations. Uh, and the first one is going to be LIMS 5 demo setup. This is basically executable file, and this is actually the Windows version of it. So you might want to use a Windows computer when you are operating with this LIMS. And that being said, all of the program and all of the inherent files with the LIMS itself is going to be directly stored under what they specify as iHome. And further, for our main examples, we are going to be studying the resin impregnation over a rectangular mold, and study isotropy and anisotropy, and also study race tracking. So for all of these, you should have to download the files that are present in Appendix C LIMS files. So these are the two primary downloads that you might want to do. Secondly, you are going to go into LIMS technical support and see that there is additional information that is available here. The main tutorials, these are like 4 or 5 minute tutorials which help you to understand what the basic filling is, if you have an absolute, no, a perfect model, a perfect mold with perfect layup, how would your simulation work, and properties of anisotropy. And we are also going to mold vents, meaning to say that you have resin injection and you have the outlet port as well. So the location of the outlet port will govern if there are voids formed at certain locations in the mold itself. So we are going to go over a little bit of that as well. And I'll talk more in detail about the meshing for the model once we get to that point. So once you get to the website, the two main areas that you want to go to are downloads and the technical support, where you can find the software itself and the documentation and some of the tutorial videos. All right, so let me go back to sharing the presentation. All right. So now, what is LIMS? Essentially, it's a software tool that is going to help us simulate a flow of the resin through a fiber fabric preform, and it is going to be a flow through a porous media, essentially. And we are going to be defining the modeling through the finite element of the control volume approach, which means that when you have, let's say, for example, a 1D model, where you have a fiber fabric preform, and you are going to discretize it into X and N number of nodes in the X and Y direction, and you are going to propagate the boundary conditions from one element to another moving forward. So we'll talk a little bit more about the meshing process as well as we move on. As I said, the main reason why we are going to use LIMS is to optimize the resin fill process of the entire mold, so that we get a quality product as well as with very good strength and the capabilities that we were looking for. And essentially, by doing this, we minimize the number of experiments that you have to run, because these experiments tend to be very expensive, as well as they require a lot of resources. For a simple Wartam experiment, for example, you would need to have vacuum pump, you need to have like different ports, you need to have like tacky tape. When you keep adding on the number of items that you need for an experiment itself, such as the distribution media, distribution media, the vacuum pump, the tacky tape, and the ports and the tubes, it does tend to get expensive. The resin itself is expensive. So that is the reason you want to minimize the trial and error process. So in this slide, I've also given the location where you have to go and download your files for the LIMS, as well as some of the simple technical examples for the simulations as well. So what are we going to get out of this this tutorial video? First thing is to learn how to use LIMS. It's a very straightforward, very user-friendly software. You just need to work around a little bit to get the hang of how to use it. The first part of understanding that we are going to extrapolate from our theoretical knowledge is that our study of isotropy and anisotropy, the way materials behave. So we are going to study the anisotropic properties of the composite that we are manufacturing. That is through a simulation. And we can always give two different kinds of boundary conditions, pressure-based boundary conditions and flow rate-based boundary conditions. So we are going to study about that as well. What would be the difference when we give a pressure-based boundary condition? What would be the difference when you get the flow rate-based boundary conditions? We are also going to introduce race tracking, where we know that the resin always tends to follow the easiest, the easiest resistant path. The least resistant path. We are going to model race tracking via that means as well. And moreover, and then we are going to see if the location of the vents at certain places is going to, govern how the the voids are going to be formed in the model or in the mold. So this is going to be the deliverables for this small tutorial. So the first, I will run over the results in the order that we are going to be performing the experiment, and then we will move on to talking about each of the specific experiments. So the first experiment that we are going to be conducting, or the first simulation that we are going to be doing, is going to be the isotropic material fill time simulation. So in this case, what we are going to do is we are going to use a square mold where we are going to inject the resin through the center point. So it is going to be the resin injection at the atmospheric condition. And as you can see that this is the time fill, and this is basically the pressure distribution. So you can see that you can see atmospheric pressure at the inlet port, and you can see atmospheric pressure at the inlet port, and as the flow takes place, you can see almost vacuum pressure at the corners where the mold is filled. You can also see here that the time that taken to fill the entire mold um, in this condition is essentially depicted in this figure. So the next part of developing from the isotropic model is anisotropic model. In this anisotropic model, we are going to observe how if when your kxx, which is permeability along the x direction, is going to be 4 times kyy, then how does your fill pattern look like? Um, so when there is when there is permeability which is going to be more in the x direction, the flow tends to fill up fast in along the x direction, and then move on to the y direction. Similarly, you will observe vice versa. When your kyy is greater than kxx, you see the resin flowing faster in the y direction, and then slower in along the x direction. So let us now see the simulation that we will be able to do using the LIMS software. So let me share my screen again. So now, as you can see, I have downloaded the software and I have installed it. And now you should be able to see the LIMS UI, which is the LIMS user interface. It is a very user-friendly, and this is version 5.0.8, and it says it should expire on December 31st. So the size limit for this kind of simulation is going to be 3,000 nodes. For simple simulations that we are running today, that should be very much enough, because we are not even running more than about 1/10, about 300, 400 nodes is what we are going to be using for our simulations for the day. So that being said, let's get started. There are 4 basic tabs that we would have to know about. The basic and execute, select and cover, that we will be using a lot. The manage views, essentially, it helps you zoom in, zoom out. The pan features that you use similar to any other software, modeling software, or any other simulation softwares that you use, like ANSYS Fluent, or SolidWorks, or Creo. The mesh display essentially tells you the different kinds of parameters that you'll be able to study, the time filling phenomena, or the phenomenon of the pressure variation. So let's now go. So once you install this, it comes with a few inbuilt files. So we are going to start with, as I said, it's going to store all of the files in the C drive under iHome. So let's start with the examples that we already know. So let's go to quick start and model1.dmp, which is essentially a square model that I was the first example that we are going to talk about. It is going to be a square mold, and the dimensions of it will be specified when we go back and open the DMP file, in which, if you remember, in any of your model creation softwares, you'd first create a model and then discretize it. So in this case, it is a structured mesh, like we call it. So you have, you have the entire length, which is going to be divided by n number of, nodes, and each of these points are called nodes, and each of these are called elements. Now the main process of running a mold filling simulation is going to be just the first three steps. Is something which has to be followed to the T. The first step for us is going to be assigning where the input of the resin is going to be, and the output of the resin is going to be. In this case, I'm going to just give the input and assume it's going to be the vacuum conditions, as absolute perfect vacuum conditions at the boundary. And and now, once we give the input condition, we have to define how the elements are, meaning to say what the properties of these elements are. In other words, defining the volume fraction as well as defining the permeability. So once we do both of these, we can then move on to the third step. The third step is where we set the properties of the resin itself. So the resin properties of resin viscosity is what we are going to set. So let's move on to the first step. For the first step, we are going to select a node, right? So the first thing that we want to do is select a node, and you want to click on this button, which is essentially selecting the button, selecting the node. Sorry. So once you select the node for your resin injection, you are going to set it as a gate. So now you click on set gate. The key parameter, the key operation here is that when you select the type of gate, you have to hold on to your left mouse button, because if you don't, it's just going to pop in and pop out. So you're going to hold on to your left mouse button and choose what we are going to have: a pressure, a flow, pressure input condition, flow rate input condition, or mixed. In this case, we are going to do pressure. And as I said, we are going to inject the resin from the atmospheric condition to absolute vacuum. So we are going to start at 101.325 Pascal. So that is going to be the input. The next thing that we're going to do is we are going to select the elements and give the element properties. So this box operation helps you select the entire boxes of the entire range of elements. So once you select it, it completely turns into red. So now what you're going to do is you're going to assign the properties of the material here. So right click and select material properties. So in this case, the thickness of the fiber fabric preform is going to be given as, a 0.001 meters, and the volume fraction is given as 0.5. And since we are going to model an isotropic, injection, a resin injection and mold filling, we are going to see with the permeability of KXX, given we are going to apply, we're going to say okay. So now we have done first two of the three steps. We've assigned the inlet node for the resin injection. We've assigned the properties of the elements. Now we go ahead and assign the resin viscosity. So we'll set the viscosity to 0.2 Pascal second. So you click on OK. Now we are all done with the pre-processing of pre-processing setup of the element. Now we go ahead and save the model, and we start running the simulation. So when you run the simulation, you can see that you can dump the entire results. You can change the file name. There is a few advanced settings. So the advanced settings is, in this case, we are going to be wanting to fill the entire mold, so that the mold is completely impregnated with the resin. Sometimes you want to see where till a specific node, right, in a long part, So in that case, you will select the node reached, or if you want to see like at a certain time how far the resin has impregnated, or how far the resin has traveled. So you choose the time limit, and you can always set the pressure limit and the flow rate limit. And in certain conditions, when I was talking about, in the bridge building contest, you'll have multiple inlet ports, and if you are going to provide the resin in a sequential manner to, obviously have, complete impregnation of the mold, you would choose sequential injection. But we are going to do the entire mold is filled, and we are going to run the simulation. So we click on show details. It is going to tell us what it basically tells us the entire loop of how it is solving. And as you can see, the set gate 61 is what we have set for that point, which is the node 61, where we have given the pressure of the atmospheric pressure. So once it is done, we click on OK. You can see that the time taken to run the simulation is essentially about 46 seconds. So essentially the time to fill is going to be 46 seconds. You can also notice here the number of empty nodes. The empty nodes is essentially where, in case if there is a void present at a certain location, it would indicate the number of empty nodes right there. So in this case, we can absolutely certainly say that we have indeed impregnated the entire mold. So once you've done with that, you can just apparently close the window, and you can see uh, the flow of the resin in the entire mold itself. You can now go and see that in the mesh display, you can see various different results. So for the first, we just saw the result, which is going to be the time to fill. We can also see the pressure. So if you see the pressure, the nomenclature that's given here, the pressure at the inlet is going to be the atmospheric pressure, and as you can see, the vacuum pressure is at most at the outlets, at the boundary of the mold itself. So now you can also see the fill factor, which is essentially to tell you like, okay, the entire mold is filled or not, or if there's a void present or not. So in this case, you don't have a void, and it is completely filled. Similarly, so now another point to touch base on is, now that the entire model is done, and if you're going to change the properties of the model and rerun the same simulation, all you have to do is just clear the results. You can choose to save the results, or you can choose just to clear the results and start over. I'm going to just show you how you would set up parameters. So in this case, if I want to set up, an anisotropic model, what I would be essentially be doing is selecting the entire elements, and you right click on the material properties, and you can actually select those planes of X and Y, and you can give different properties here. So let's say if KXX is going to be 4 times as that of KYY, and then you basically go ahead and give your point of injection, where it's going to have a pressure condition. Once you give, then you set your viscosity, which is already set here. You go and save and run the simulation. So you can see here that we have set the node at 61. You have seen the pressure that is set, and you can see that the mold filling is happening according to the anisotropic nature of the composite itself, or the fiber fabric preform. And in this case, you would see that the time taken to fill is about 25 seconds. And you have absolutely no empty nodes. So this is almost half the time that it needed to fill in the isotropic material, in the isotropic properties itself. So properties of the preform itself. So that being said, you can optimize your layup as well, based on the fill time that you would see in the simulation itself. All right, so that is our first part of the demo. I would highly encourage you all to try it out. It is fairly simple, but you might want to try a couple of times to get a hang of it. The next part is where we are going into a real-time simulation of a mold with race tracking and anisotropy and so on and so forth. I will talk about that in just a second. Let me stop sharing and we'll talk about it. So we are going to study through the case studies. The first case study that we are going to be doing with LIMS is going to be example 8.15. It's in your textbook, it's page 480. And in this case, you have a rectangular mold cavity. You have the length of the fabric to be 620 millimeters. You have the breadth of the fabric to be 200 millimeters. You have the entire mold length to be 700 millimeters. So the first step is when you are modeling something like this, you will first model, let's say you're modeling going to be in SolidWorks, you will model with the given specific dimensions, and then you would go about discretizing it either in SolidWorks or a software called Gmesh, which is also downloadable from the LIMS website, from the University of Delaware LIMS website that I showed you before. So you should be able to do that as well. And but in this case, we already have this model that has already been saved from the appendix C files that we downloaded. We would go over the meshing in the following demo, but in this case, to get yourself familiarized with race tracking, all we are going to do is use the existing model with the predetermined nodes and elements, and run the simulations to see the mold filling time. So in this case, we are going to have an injection gate, a ventilation port, the injection pool with the resin, and the ventilation pool. You have the fiber fabric preform. So essentially what we are going to see is, in this case, we are going to give the boundary conditions with the flow rate. So the flow rate is going to be 2 centimeter cube per second, and you are going to describe the resin viscosity, the fiber volume fraction. We're also having the permeability. I'll talk about the subscript A in just a second. These are essentially the factors that we will input in the simulation itself. The reason I told you I'll talk about this, the subscript A, is that when we model the mold itself, we are going to divide the mold into 3 different parameters. The first, 3 different zones, sorry. So the first zone is going to be the zone where there is going to be the injection and the ventilation. Here, it is supposed to be a pool, so hence we will not see the fiber volume fraction here of the pool is supposed to be 0, and the pool has the permeability of the XX and the YY is the same. It's at 4 into 10 raised to minus 7 meters squared. Now, for the first case, we are not going to be defining zones A and B, where we assume it is a perfect mold. And so we will have the Ka equals Kb, and we have the volume fraction of A equals volume fraction of B, which is going to be 0.4. And for the second condition, we are going to have medium level race tracking, in which you would be able to see, 2 different kinds of, we're going to set 2 different boundary conditions of different volume fractions in the zones A and B, and correspondingly different permeability values in zones A and B. And in the third criteria, we are going to see the volume fraction of A and B to be different, as well as the Kb is going to be 100 times of Ka. So this is essentially the simple VARTM or RTM setup that you might have seen or you might have done. So essentially, you are going to have the resin inlet through gate 1, and you are going to have it's vacuumed from the right end, which is going to be the vent. So that being said, let me see. All right. So some of the steps are also given here, but we would go ahead and do the demo for y'all, so that yeah. So before going on into depths of doing the demo, from our basic understanding of the physics of flow through porous media and the phenomena of race tracking and voids being present, we understand that when there is, it's a perfect mold and it's perfect vacuum condition and perfect injection, we see the mold filling pattern to be very linear. But when you see that there is going to be a difference in the permeability as well as in the volume fraction of the material of the fiber fabric preform, we know that the resin tends to take the least resistant path to move forward and quicker. So in this case, you will see the race tracking effects, and you will see how the resin is moving through the fiber fabric preform. When there is a vast difference in the nature of the preform itself, you will see that you would observe sharp trends in the zones between zones A and B when with the flow of the resin itself. So why do we need to study this? So we need to study this the flow pattern and the flow time taken to understand what kinds of pressure we are dealing with. So the injection pressure, because it's a flow rate boundary condition that we have given, how does the injection pressure vary at different, at different uh, ratios of Kb over Ka, which is the permeability of the two different zones. So how does race tracking affect the pressure, the injection pressure itself? So this is essentially um, you know, our takeaway from the entire experiment itself. So now let's move on to working out this experiment using the LIMS software. So let's now dive into the example 8.15 in the textbook, and let's use LIMS to simulate the example. So the first step is, after you download all the files from Appendix C, you should be able to go to File, Open, and you should be able to see, let me go back a couple of steps. You should be able to see the Appendix C under iHome folder, so Appendix C, LIMS, files. So under that, we are going to work out an example 8.15, and it has 3 different scenarios. Let's work out the first scenario and the third scenario, and I'll leave it up to you guys to work out the second scenario. So for the first scenario and the third scenario, we will be using the same file, the same parent file. So if you see the 815 example, there are 2 different files. There are multiple different files that I have saved over different iterations, but there are 2 different files that I wanted to show you. S1.dmp is the file that we will be loading to create our simulation, our flow filling model. The rectangle.dmp essentially it is essentially a file with the coordinates. So as you can see, the number of nodes here is about 396. You can see x, y, and let me pull it up a little bit more. You can see x, y, and z coordinates and the number of nodes in here. Something that you want to keep in mind in the future when you have to design a model and discretize it and upload it in LIMS to conduct a simulation. You want to remember that the maximum number of nodes right now is about 3,000. So in this simulation, we are barely using any of those. About 1/10 of the nodal points is what you're using. So you go to S1.dmp and you click it. It opens up the rectangular mold with about 700 millimeters in length and 200 millimeters in the width. The first thing that we do is we are going to select the inlet gate. So as specified in the problem statement, we are going to choose inlet be middle, which is going to be with coordinates 0, comma 0.1. And once we set it, it is going to be set with the flow rate, not as a pressure. And the flow rate is specified in the problem statement itself. It's going to be Q centimeter cube per second. So once you have that, you have set the initial gate. The second that we want to do is we want to set, in the scenario one, we want to set the injection pool and the ventilation pool, basically the parameters for it. So you would go about and select these two set of elements and these two column of elements. So once we select the column of elements, right click anywhere on the screen and set the material properties. So the thickness that is specified in the problem statement is 5 millimeters, and that is visible here for us. And it is going to be isotropic, and the volume fraction is essentially 0. Because it's a pool of resin, and the permeability is given as 4 into 10 power minus 7 meter squared. So you click on apply, and the reason that I wanted to show you this is you cannot have the value of the value of fiber volume fraction has to be between 0 and 1. So you have to give a value such that it is with a certain number of zeros. You just give 1 and click on apply, and it should work, and say okay. So now we move on to selecting the other zone and providing the material properties of the other elements. In this case, we are not going to study the race tracking phenomena, and hence what we are going to do is we are going to assign the same material properties for the entire section of the mold. So you can click on anywhere, select on material properties. The thickness is going to be the same. It's going to be 5 millimeters. The volume fraction is going to be 0.4, and the permeability kxx, and it's going to be equal to kyy because it's going to be isotropic. And we are going to choose 4 into 10 power minus 10 meter squared. So I would ask you to think about another phenomenon when you have an anisotropic layup. How would the fluid flow be? So this LIMS software comes handy in here, where you can select your orientation of the fibers based upon how your results are from this methodology of learning to understand um, your liquid injection molding. So you click on apply and say okay, and then now we have set all the boundary conditions that are necessary, and we have uh, the final item in our checklist is going to be to set the viscosity. The viscosity is given as 0.1, and we set the viscosity, and we are good to go. So now we are good to run the experiment. So the first thing we do is save it, and then you run it. And we want to wait till the entire mold is filled, and then you start running it. As you can see, it forms, it's basically a code, and it is going to run and provide us with the time step model itself. Something to note here is the time to fill the entire model is going to be around 225 seconds, and there are absolutely no empty nodes, meaning the mold is completely filled. So you can see the simulation of the flow of the resin through the mold in this particular phenomena. You can see how long it takes for the resin to reach from the initial location to the final location. Similarly, if you go into the mesh display, you can also see the pressure variation, as you can see that it is a pressure-driven flow through a porous media. So and due to the virtue of change in pressure, you can see what the injection pressure is for the given condition without any race tracking. As you can see, it's about 3.1 into 10 power 5, and you can see how it is flowing through the media itself. So this is the first exercise to depict one of the very standard problems for example, in bottom molding in Vatam, or so on and so forth. So that being said, I would leave up to you guys to do the second model, which is going to be medium race tracking. But we will touch upon the third model right now. So to go and change your model is you click on this to clear the results. So if you want to save it, you can save it. But now I'm just going to rerun it without saving the results. So the first thing that you would do again is to set the for us to set the injection port, which is going to be in the center, and we are going to set the gate, and it's going to be the flow rate. It is again going to be 2 centimeter cube per second, and then we are going to choose the elements. So in this case, we are going to have 3 different pools, right? So if you remember from our textbook, so let me go back down here. You see that this is going to be C, this is going to be B, this is C, and this is A. So now we are going to start into race tracking. So we are doing the scenario 3 right now. So the scenario 3, we have the volume fraction of B as 0.25, the volume fraction of A is going to be 0.1, and you see that the permeability of Kb is going to be 100 times as that of Ka, right? Ka is given as, if you remember, Ka is given as 4 into 10 raised to minus 10 meters squared. So in this case, let's go back to LIMS. So now we initially set the C zone. So these 2 columns and these 2 columns will be our zone C, and we can set the material properties. As I said, set it as 0.000 with a lot of number of zeros and 1, and the kxx is 4e to the e raised to negative 7 meter squared, and we click on apply and say okay. And then the next part is we are going to select the zone B. Again, it's very simple for us to select zone B. Once you have this icon, which is add to selection on, you can keep selecting as many number. So then once you select it, once you select the whole B zone, we can right click and give the material properties. The material properties, in this case, we know that the B zone has the material properties of Vf is equal to 0.25, and we know that the B is going to be, the Kb is going to be 100 times as that of Ka. So in this case, the permeability is 100 times, so it's going to be e raised to negative 8, and then you say apply and you say okay. So once this is done, we are going to select the A zone. The zone A is going to be selected, and we are going to provide the material properties for zone A. In this case, our volume fraction is going to be 0.1, and the Ka remains constant. It's 4 into 10 raised to minus 10. You click on apply, you say okay, and now that we've given all of the conditions for the elements, we go and set the viscosity, which is going to be 0.1 pascal second, and now we are good to run the simulation. So we save the model and we run the simulation until the entire mold is filled. So now it is running the simulation, as you can see, and as you can see, you can observe due to the changes in the permeability and the changes in the volume fraction along the edges of the mold, you see how the flow is behaving. And now you see that the time taken for the entire flow to happen is about 309 seconds, right? In comparison with the case 1, where it's perfect mold, it's about 225 seconds. So, and then you can also visualize the pressure. You can also see that at this point you are going to see lower pressure occurring, and you will also be able to see the fill factor and see like there might be would there be any possibility of voids, but apparently we observe that all of these values still fill factor is essentially how much of the control volume is filled. It's essentially saying that you will have, and the ratio varies from 0 to 1, is essentially saying the fill factor is 1 throughout the model itself. But due to the race tracking issues, there might be a slight dip in the in the control volume filling at these two regions. So now, if you want to improve, the filling, improve the impregnation, what do we do? Do we give multiple inlets, and do we give multiple ventilation ports, etc.? So that concludes our LIMS presentation for the example 8.15. Please feel free to try out um, the second part of the problem, and also try out the anisotropy with the given condition. So now let's move on to the final section of the first demo. Let me share my screen right now. All right. So the last section of the demo, in this model, I'm actually going to simulate an actual Vartam experiment that is conducted in the lab, in which case you are going to have two different inlets and one venting. This is essentially depicting what we will have in our actual setup, where you apply the vacuum, and then you have another pipe connecting to a resin trap, which essentially takes out the excess resin after filling the mold. So we are also going to see what the fill factor is, and we are also going to see the pressure distribution along along length of the mold. To do so, I'm going to use the same model that we have been using, the S1 model .dmp. And as you can see, I'm going to select two different locations as my inlet. So I am going to, in this case, I'm going to give a pressure condition, pressure boundary condition, and I'm going to inject the resin at atmospheric pressure. And further, I'm going to say that there is going to be one venting location. So in this case, I'm going to set the pressure to be 1/10 of that of the as that of the inlet, so which is going to be about 10,000. So once these are set, I'm going to go ahead and assign the zones. So similarly, we will have the ventilation pool and the injection pool, and we are going to have the properties as 0.0001, and the properties of permeability apply here, and say okay. And now excuse me, I'm going to apply the material properties of the fiber fabric preform, and I'm assuming the mold is perfect without any race tracking, and I'm going to assume it's going to be isotropic. I'm going to assume a volume fraction of 0.4, and the kxx is 4 e raised to minus 10 meters squared. I'm going to say apply and okay. And here I'm going to set the viscosity as 0.1 pascal second. So once I'm done with this, all of our initial pre-processing conditions have been set. So now for our node to be considered as a vent, we've got to go and edit the script. So this is what is going to be different. So as you can see, we're going to see the simulation until the entire mold is filled. But we are going to go ahead and edit the script here which says, as you can see, I have given a single node with lesser pressure. So in this case, I'm going to change this number to 5, which categorizes the node to be a vent instead of an injection port. I'm going to save it, um, or I'm going to save it with a specific file name, or in this case, I'm going to leave it and run it for the sake of time. And once I'm going to start to run, you can see here the gate has been set as venting, and you can see how the rest of the other two inlets are set as the injection ports with a higher pressure. So once I set OK, so you see that the time taken for the complete fill to happen is around 383 seconds. So once this is done, what we are going to do is we are going to see um, the plots of the fill factor. So you can see the fill factor with the injection port, the fill factor is varied. And you can see that there are regions where the fill factor is about 0.99, still close to 1. But in this case, it shows that the lesser control volume filled in those regions of lighter colored regions. And you can also see the pressure. As you can see, the pressure gradient varying. So in this case, you will see from the atmospheric pressure and going up to about 1/10 of the pressure of the atmospheric pressure. So this is the final part of our demo. I'm going to stop sharing the screen and all right, so that was the conclusion of the 4 different models that we were planning to do as a part of demo 1. The first demo 1 is essentially for you to familiarize with the software, try to play around with whatever inherent model is available in the software itself. In the next class, we will start, in the next demo, we will start with using GMesh with LIMS. So you can find this essentially under LIMS technical support, and this is a video in itself. And you have the GMesh software that they have actually embedded, so you can download it. It's an open source software. You will be able to get a CAD model, and you can actually mesh the model, and we will be able to see if by refining the mesh, do we get better results or not. So this is going to be part of our demo too. But for the first part of the demo, I would like for you all to look into the simple filling problems and try to play with anisotropy and try to run the scenario 2 that was given in example 18.5, and also and start with seeing if you can model your vents by changing the number that was given in the script to 5. And finally, I would suggest that if you could do these 3 tutorials in addition to what has been done in the demo, one, the running simple filing simulation and running simple filling simulation and running simulation with anisotropic permeability and modeling vents in LIMS UI, that would be a very good start for us to go ahead and learn the other tools of using other tools and GMesh embedded with it. So start off with downloading the LIMS software and all of the files that are associated, the Appendix C files and the LIMS software, and then finally go up to the technical support and download the rest of the documentation. And we will talk more about GMesh in the upcoming class. If you have any questions, please feel free to reach out to me. You have my email ID, or you can email me through Blackboard. And thank you very much.